In the previous video, we used the factorial symbol to organize our calculation of the number of ways to arrange distinct objects in a row. As we will learn in this video, the factorial symbol continues to be helpful even when the objects we try to arrange are not all distinct. We start by reviewing the previous case of distinct objects and then consider what happens when some objects become indistinguishable. How many patterns can we construct by arranging 3 different letters and 2 different numbers? Since A, B, C, 1, and 2 are all distinct, there are 5 factorial equals 5 times 4 times 3 times 2 times 1 equals 120 ways. There are 5 places to put the letter A, 4 places to put the letter B, 3 places to put the letter C, 2 places to put the number 1, and 1 place to put the number 2. As a follow-up to the question that we have just answered, how many patterns can we construct by arranging 3 identical letters and 2 identical numbers? Do you think it's more than 120 ways, exactly 120 ways, or fewer than 120 ways? Please pause the video to consider this question. There are fewer than 120 ways, in fact only 10. They are as follow. The leftmost number could be in any position except for the slot at the right. It might be all the way to the left, leaving 4 positions that the rightmost number might take. The locations of the letters are thus constrained. If the leftmost number is not in the leftmost slot, it might be in the next slot over, leaving 3 positions that the other number might take. If the leftmost number occupies neither the leftmost slot nor the next slot over, it might be in the middle slot, leaving 2 positions for the other number to take. And finally, the numbers might occupy the 2 slots farthest to the right. These are the 10 ways to arrange 3 identical letters and 2 identical numbers. Each pattern of shapes, for example square, circle, square, square, circle, corresponds to 12 arrangements that would be distinguishable if the letters and numbers themselves were distinct. There are 3 places to place the letter A while conforming to this shape pattern. There are 2 remaining places to put the letter B, and 1 place to put the letter C. There are 2 places to put the number 1, here or here, which constrains the final place that the number 2 can take. 3 times 2 times 1 multiplied by 2 times 1 equals 3 factorial times 2 factorial equals 12. How many ways can I arrange 3 letters into the 3 slots with blue question marks? There are 3 factorial equals 3 times 2 times 1 equals 6 ways. How many ways can I arrange 2 numbers into the 2 slots with golden question marks? There are 2 factorial equals 2 times 1 equals 2 ways. If the letters A, B, and C were indistinguishable, and the numbers 1 and 2 were indistinguishable, then these 12 patterns would be indistinguishable. Thus, in this sense, they belong to the same family, the family defined by the theme square, circle, square, square, circle. This other theme, square, square, circle, square, circle, corresponds to its own family of 12 patterns. And here's another theme with its own family of 12 patterns, and so on. The number of families, or themes if we like, multiplied by the number of patterns per family equals the total number of ways to arrange A, B, C, 1, and 2 in a row. Dividing both sides by the number of patterns per family, we say that the total number of patterns divided by the number of patterns per family equals the number of families. In this example, there are 3 plus 2 factorial equals 120 patterns of A, B, C, 1, and 2, and 3 factorial times 2 factorial equals 12 patterns per family. So there are 10 families. More generally, L plus n factorial over L factorial n factorial is the number of ways to arrange L indistinguishable letters and n indistinguishable numbers in a row. Another way to describe this quantity is to think of it as the number of combinations or ways in which we could grab L objects from L plus n total distinct objects. To understand this perspective, we relabel the icons on the slide. Rename slot 1, slot 2, slot 3, and so on, thing 1, thing 2, thing 3, and so on. Where you previously said the word square or letter, speak the word grabbed, and where you previously said the word circle or number, now speak the words not grabbed. We might have originally read the example shape pattern at the top, slot 1 square, slot 2 circle, slot 3 square, slot 4 square, and slot 5 circle. But now we say thing 1 grabbed, thing 2 not grabbed, thing 3 grabbed, thing 4 grabbed, and thing 5 not grabbed. This sequence of words represents one possible outcome of placing L plus N things into a container and then dipping your hand in to grab, in one swoop, L many things while leaving N many things behind. Our declaration that the different letters A, B, C, and so on are indistinguishable, and just as well all regarded simply as square or letter, is equivalent to a declaration that we don't care whether we grab thing 1 first and thing 3 second, or instead grab thing 3 first and thing 1 second. In the same way, our declaration that the different numbers are indistinguishable is equivalent to a declaration that we don't care in which order things were left in the container. Each distinct combination of L things that could be grabbed in hand corresponds to one pattern of squares and circles in a row. Counting the number of patterns of squares and circles in a row is equivalent to counting the number of combinations of L things that can be grabbed from a container of L plus N distinct things. So as we claimed, the quotient L plus N factorial over L factorial N factorial is the number of combinations of L things that can be grabbed from a container of L plus N distinct things. Now that we have introduced combinatorics, we can apply it to derive the binomial theorem in the next video.